L'Hopital's rule. This is an alternative way of doing limits from what we did previously in the year, which was evaluate limits analytically. What I mean by analytically is for instance, for the first example here, we crossed out the whole. In the second example, well, we're straight out of luck in that one. The third example, we could just look at the ratio of the leading powers, and we know we get 3/2 here. And our fourth example down here, example 3, we'd say the power on top is bigger than the power on the bottom, so that thing's going to infinity. So we already have tools to solve some of these, but as you can see with example 2, we don't really have a tool for this yet. Tangent of 0 over sine of 0, both of those go to 0, and we don't know which one goes there faster just by looking at it. So we're going to go through and solve these questions and see how L'Hopital's rule also gets us to the answer we want. So the first step of every L'Hopital's rule problem is to make sure that you have a 0 over 0 or an infinity over infinity case. You cannot use L'Hopital's rule unless it has one of these attributes. Now it can be negative infinity over infinity or negative infinity over negative infinity or any of those combinations, but as long as you have some sort of infinity over some sort of infinity and 0 over 0, this is a legit method. So in this one, say you don't notice that there's a hole and you want to solve this a different way. What you do is you just take the derivative of the top and take the derivative of the bottom independently and now reevaluate the limit. And if you do that, you get that it's just 4. You just plug in 2. Limit as x approaches 2 of 2x, which is 4. So pretty powerful. I didn't have to factor out the x minus 2x plus 2 on top and then cancel out the x minus 2's for the whole and figure out that it was going to 2 plus 2, which was 4. I could just do this. A little bit easier. So let's try our next one. We're going to keep our limit. And I'm going to take the derivative of the top and the bottom independently. So 3, the derivative of tangent is secant squared. And I forgot the 3 there. This 3 out front is for the chain rule, for the inside. And our derivative of our bottom is 2 cosine 2x. All right, so now I got to think about what this is now. So I have this 3/2, so I'm just going to pull that out. And I forgot my limits. So I'm going to put that in here. So 3/2, and then secant squared of 3x, well, that's just 1 over cosine squared of 3x, because secant is 1 over cosine. So really I have a 1 over cosine squared of 3x times cosine of 2x. And I'm going to plug in 0 now. Well, the handy thing about this is cosine of 0 is 1, so we just get 3/2. 1 over 1 is 1, times 3/2 is 3/2. Sweet, we did it. So this thing actually goes to 3/2, so it's like these were 2 lines, like the tangent and sine being there didn't even matter, which is kind of cool. Alright, our next one. I check infinity, I see that it's infinity over infinity, I'm allowed to use L'Hopital's on this. And I take the derivative, I get 6x plus 5. Over, and I forgot the limit. 4x minus 3. So 6x plus 5 over 4x minus 3. Still infinity over infinity? Well, we can L'Hopital's again if we want. Now, we know ratio of the leading terms. It's going to be 6/4, which is 3/2, which is the same as we would have gotten from the first step. Kind of showing that this works and is consistent between the steps. So I go again, limit as x approaches infinity of 6 over 4. The 5 and 3 go away and the x's go away when we take the derivative. And we can see that there's no longer an x in the problem, so we're going to 6/4 or 3/2. Sweet. And our last example. We have infinity over infinity because 3 times infinity cubed over 2 times infinity squared, that's infinity over infinity. And so I'm allowed to L'Hopital's this, limit as x approaches infinity, of 9x squared over 4x. Okay, still infinity over infinity. I'm allowed to go again. 18x over 4 is what I get. So 9x squared's derivative is 18x, 4x's derivative is 4. Okay, I no longer have infinity over infinity. If you take another derivative, not only will you be disappointed because you get 18 over 0, but you're going to be saddened also that that's not legit. That's not a thing. So now we just plug in infinity and we get infinity. So we can see that this limit goes to infinity, which we could have already discerned at the beginning by seeing that the power on top was bigger than the power on the bottom. And that's L'Hopital's rule. Now we use this for more complicated examples. For example, example 2 here is the kind that you might see as a spot on the AP test where you have to use L'Hopital's rule to solve the question or remember the property. But L'Hopital's rule is the easier way to go. And that's it.